In this video, I want to talk about one of my favorite topics in graph theory. I have spent 10 years doing research about it, and it culminated with my PhD thesis. It involves graphs and their representations. By a graph we mean a picture like this, so it consists of nodes, also called vertices, which are connected by edges. For example, you can imagine cities on a map which are connected by roads, or a social graph where nodes are people and connections are for friendships, or a chemical compound where atoms are connected by bonds. But of course, not all drawings are equally good. The structure here is not understandable, but if we draw it in a better way, it is immediately revealed. So ideally, we want to obtain the best possible drawings. In this video, we will discuss a different kind of representation where graphs will be represented by intervals. I have left academia after finishing my PhD in 2017, but I'm still using the results and the approaches I learned there even nowadays. So I'm working on this application, on this web application called OrgPad. You see right now, and I will be using it also for my presentation. It allows one to build a knowledge network where you put information in form of a graph, and you can see the graph visually, you can play with it, and you can improve your understanding. So I have prepared my presentation in this form. So let's get into it. So we are going to talk about interval graphs. And the idea here is that we will represent vertices by intervals and edges will be described by their intersections. So if I have two vertices which are adjacent, for example P and Q here, their intervals are intersecting. On the other hand, non-adjacent vertices are represented by disjoint intervals. And we say that a graph is an interval graph if it has some interval representation. Of course, not every graph can be represented in this way. For example, a cycle of length 4 or more is not an interval graph. And the argument goes like this. We start with the subpath and we look how it is represented. So the red vertex is represented in some way, and say the blue one is drawn next to it. Then green one is forced to look like this, yellow one is forced to look like this. But now it is no longer possible to add the last missing vertex, because it should intersect the red one and the yellow one and skip over all the vertices in between. But that's not possible. So cycles cannot be represented by intervals. Similarly, the subdivided star cannot be represented by intervals. The red vertex is represented in some way, and it has three neighbors: blue one, yellow one, and green one. Now we can add neighbors for blue one and green one like this, but it is not possible to add the purple neighbor, since the entire yellow interval is covered by red one. So adding the purple one is no longer possible. So this is not an interval graph. But we can use these results to actually show more. Suppose that we start with some graph G and we remove some vertices. We obtain an induced subgraph. If G is an interval graph, then this induced subgraph is also an interval graph. So interval graphs are closed under induced subgraphs. This corresponds to removing intervals from an interval representation. We can view this implication in the opposite way. Suppose that we start with some induced subgraph G prime, which is not an interval graph. Then it follows that the entire graph G is also not an interval graph. So for example, every interval graph cannot contain this subdivided star. We can use this to characterize trees which are interval graphs. If a tree doesn't contain this as an induced subgraph, it has to look like this. It consists of a central path to which there are some leaves attached. And we can represent this by intervals. First we will represent the central path, like this. And then we will add the leaves to each of the vertices. So red one, blue one, green one, yellow one, and purple one. And these trees have a special name. They are called caterpillar graphs because they sort of look like this caterpillar animal. So there are sometimes quite funny names in graph theory for various types of graphs. And we have just proved that interval graphs, which are trees, are caterpillar graphs. And we also know that cycles are not interval graphs. So there are no induced cycles in an interval graph. And such graphs without induced cycles are called chordal graphs. This is not a chordal graph because there is an induced cycle of length 4 here. But we can fix that by adding one edge. And this edge is called a chord of the cycle. And this is why the name is called chordal. That every cycle of length 4 or more has at least one chord. So this is a chordal graph, but as we will see later, it is not an interval graph. So chordal graphs are a superclass, they're more rich. Geometrically, chordal graphs are intersection graphs of subtree in a tree. So unlike interval graphs, they allow branching in different directions. Before we go any further, let's take a look at the origin of interval graphs, how they were actually discovered in the history. So they were first considered by Hungarian mathematician Hayos, who introduced them in his 1957 talk, which we don't know what was there exactly. We just have an abstract from this talk, so I have translated this from German if you're interested. But both the motivation is not clear and also what actual results were presented. Interval graphs were independently discovered by Benzer 2 years later in his beautiful study from 1959. Benzer was originally a physicist, but he got interested in biology, and nowadays he is considered as one of the founders of evolutionary genetics. And this is a beautiful paper which studied what is the topological geometric structure of genetic information, how genes are stored, at time where people didn't really knew how this looked. Nowadays we can of course take some microscope and take a look at the structure and we can see everything. But in 1959 this was not yet known. So Benzer approached the problem as a physicist. He took the simplest possible organism on which he could study genetic information. And so he studied bacteriophages, which are viruses which attack bacteria. In particular, Escherichia virus T4, which attacks the Escherichia coli bacteria. And as it sometimes happens in research, his main discovery was actually a complete accident. When you place a normal strain of the virus in a petri dish, you will see a visible plaque. But if he placed some defective mutants, the plaque was not visible. And when he saw this, he was like, wow, I can actually use this to build a detailed genetic map of the virus. His idea was to run experiments with pairs of defective mutations. Now, when these mutations are non-overlapping, so they are changing different parts of the genetic information, they can recombine together back and they can fix the defect. So they can produce the original undefective version. So the plaque was visible. On the other hand, when they were overlapping, like this, no matter what they were doing, they couldn't recover the shared part. So the plaque was not visible. So he could run all these experiments with different pairs and put them together and try to derive further geometric information about the possible locations of the mutations. These are his data for 19 different mutations. In his paper, he didn't consider graphs. He was describing everything in the language of matrices. So he put 0 when they couldn't recombine the original undefective version of the virus. So they were overlapping, and 1 when they were non-overlapping. And he was able to obtain an interval representation for this matrix, or in the language of the graph for this interval graph. So these 19 mutations, when you considered different pairs, all pairs of them, and you put this information together, he obtained an interval representation. So it gave him nice evidence that that actually the structure of these mutations is linear. He actually ran many more experiments. He was considering 145 mutations. So he had to do about 10,000 different experiments. He built a large matrix out of it, and he was able to construct an interval representation for all of these mutations. So he was able to get a sort of Occam-Razor type of argument that, okay, maybe the situation is actually more complicated, but for the data he got, it was not necessary. So by Occam-Razor, we should just consider the simplest model, which is sufficient to describe the data. And that was the linear model. So that gave quite a good evidence that the structure is linear. And nowadays we of course know that this is the true. Further, Benzer identified in his paper 2 structures which cannot appear in this linear model. So we have already seen the cycles are not possible, and he also presented branching, which is a slightly different graph, but this graph is also not an interval graph. And he asked the question, what is the characterization of interval graphs? Basically in the language of matrices, but we can think of it in the language of graphs. So basically whether there are some other patterns which are forbidden, and whether we could decide for a given graph whether it's an interval graph or not. And when mathematicians saw this, they immediately got interested in the problem, and they saw possible applications in biology, and later other areas were also considered. So interval graphs nowadays play an important role in scheduling and time reasoning and psychology, and in many other areas. So it's both a beautiful class of graphs, and also it is a really important one. And so further mathematical results were created quite quickly. In just 3 years, Lekkerkerker and Boland were able to characterize minimal forbidden induced subgraphs for interval graphs. We have already seen that cycles are not possible, and the other 4 graphs here so we have seen the second one, but the other 4 are the so-called asteroidal triples, and they forbid branching. So let's go back to our chordal graph. This graph is not an interval graph, and this can be argued as follows. Let's consider these 3 highlighted vertices. They have to be represented by some intervals in some ordering. Let's put red, green, and blue, like this. And we have also highlighted 3 paths going between each of the pairs. Okay, we can represent the yellow path like this, and the purple path like this. But now it is no longer possible to add the orange path, because the orange path should cross from red to blue, but it avoids green and all of its neighbors. So this is an example of an asteroidal triple, and interval graphs are intersection of chordal and asteroidal triple free graphs. Asteroidal triple is this, in general, this subgraph which contains 3 vertices, such that there is a path going from one pair which is missing neighborhood of the last one, and so on. So we have 3 paths always avoiding neighborhood of the opposite vertex. And these are minimal asteroidal triples which do not contain an induced cycle. But now let's consider a different approach. If we have some collection of intervals of the real line, which are pairwise intersecting, it follows that there is a common interval which lies in the common intersection. So, for example, I have 4 intervals here, each pair is intersecting each other, then the intersection of all 4 is this interval x here. In the language of interval graphs, when we have some clique, the clique is consisting of pairwise adjacent vertices, so their intervals are pairwise intersecting. By Helly property, in every interval representation there is some common intersection for the clique. So when we have a maximal clique, it has to be placed somewhere. For example, PQR is maximal, we can't add any other vertex into it. And in the interval representation on the right, the common intersection is this interval A on the right. Next, if we consider another clique, PQUST here, then this clique is again intersecting in some interval, and so on. So we have cliques ordered from left to right like this. So there is the C clique, D clique, E clique, and F clique. There are 6 cliques, 6 maximal cliques in this graph, and they are ordered from left to right. And by the way, 2 interval representations are considered different if their left to right ordering of cliques is different. Of course, we could always just like tweak the representation a little bit by shifting endpoints just slightly, but this is not that structurally important. So it's just better to just consider different representation for different orderings of cliques. For a general graph, finding maximal cliques would be difficult because there might be exponentially many of them. But in case of interval graphs or even chordal graphs, there are actually at most n maximal cliques, so they can be found really quickly. And this is related to something called perfect elimination scheme. It can be found by modification of the BFS algorithm for searching of the graph, and the modification deals with ties. So when you have one layer in a BFS, you put some ordering on the layer based on lexicographic ordering. And it can be actually shown that you just run this lexicographic BFS and then you go back in the order and you obtain maximal cliques easily from that. Okay, so going back to interval graphs, we can actually use orderings of maximal cliques to characterize them. And the correct property is that for every interval U, its maximal cliques have to appear consecutively as one block in this ordering. So the situation is that first we have cliques without U, then we have all the cliques with U, and then the rest of the cliques without U. So all the green cliques appear as one block. And Fulkerson and Gross in 65 characterized that a graph is an interval graph if and only if there exists some consecutive ordering of its maximal cliques. Further, this led to a polynomial time algorithm for deciding whether an input graph is an interval graph. The constraints can be described in the form of a matrix. So we have an incidence matrix between maximal cliques, which are rows in this case, and vertices, which are columns. And the goal is to reorder the rows in such a way that each column becomes 0, 0, 0, then 1, 1, 1, 1, 1, and then 0, 0, 0. So this is an example of a correct reordering, and we can use it to build an interval representation like this. We will just draw the cliques in the correct ordering, and then we will draw all vertices or intervals on top of their cliques. So P is on top of these 2 cliques, Q similarly are on top of A, then we have S on top of B, C, D, and E, T similarly, and then U, V, W, X, Y, and Z, like this. And this gives a valid interval representation. On the other hand, we already know that cycles are not interval graphs. So if we consider the situation for the 5 cycle, it has 5 maximal cliques, and the matrix looks like this, and no matter how you reorder it, at least one of the vertices will be split. So in this case, U cliques for U do not appear consecutively. We have 1, 0, 0, 0, and 1. Okay, so we have seen two different characterizations of interval graphs, in particular the beautiful relations with orderings of maximal cliques. Now we will discuss that these orderings are related to a tree data structure. And this idea comes from Booth and Lueker from 76. This is also a very nice paper. I recommend checking it out. And so basically what they did is they constructed some tree which represents all of these solutions, all consecutive orderings for the given input constraints. Maximal cliques are placed into leaves of the tree. In this case we have maximal cliques A up to H. And we obtain one ordering by reading them from left to right. So A up to H here, and the other ordering here. We can also reorder the inner nodes. So the inner nodes can be reordered to obtain other orderings. For example, the left PQ3 can be reordered to the right one. Both of these orderings belong to the same input constraints. They are solutions for the same input constraints. And the reorderings are for P nodes. We can arbitrarily reorder their children. So there are k factorial different orderings. But Q nodes are much more restrictive, and we can either keep the ordering or flip them, so do the complete reversal of the ordering. And so what they were able to show is that for every input for every constraints input, either there is no solution, so the PQ3 will be empty, or it exists and it fully describes all correct solutions, and further it can be constructed in linear time. So this solved a long-standing open problem whether interval graphs can be recognized in linear time. So let's just take a look at some examples. The paper is basically using these replacement patterns that if the highlighted subtrees should be put together by the next constraint, then we will just split it into a separate sub-P node like this. So there is a lot of patterns, replacement patterns like this, and you just apply them and you iteratively build a tree which satisfies more and more of the input constraints. So let's consider our example. So we have a graph with 6 maximal cliques A, B, C, D, and E and F. Initially we don't have any constraints, so all 6 factorial possible orderings are possible. Now let's add vertices one by one. So we start with vertex P. P is contained in maximal cliques A and B. So they have to appear consecutively together. So we have to move them out of this P node into a new P node which basically puts them together. So now we can reorder A and B, and we can also reorder C, D, E, F and this P node. But A and B always appears together. Let's continue. Okay, Q doesn't add any other constraint, R also doesn't add anything. But then we get to S, and now we have to put B, C, D, and E together. So what actually happens is that, because we have like two subtrees, we have like AB subtree and BCDE subtree would be, and they have to be like merged together. So what happens is that this is replaced by a new pattern, which is a Q node. So we have A, B, and the CDE subtree in the middle. And you can flip it in any order, and you can place F on either side. So this is now the resulting PQ3. T also doesn't add any constraint, U doesn't add any constraint, V, W, and X. But next we will get to Y, and it puts E and F together. And now we have to actually collapse, so almost everything is put into a single Q node, like this. So now E and F appear together, and CD can be swapped. And this is now the final version because the last vertex doesn't put any constraints. So this is the resulting PQ3, which describes one consecutive ordering, but it actually describes all possible consecutive orderings at the same time. Let's take a look. So we have this PQ3, and it corresponds to this interval representation we have already seen. But we can also flip the Q node. If we flip the Q node, Now the ordering from left to right is F, E, C, D, B, A. So we sort of flip like the main structure in the representation. But we can also flip the P node, which corresponds to swapping C and D. So we are swapping vertices V and W in the representation. And we can also swap the P node on the other side. And between these two top interval representations, we can go by flipping the Q node. So there is a diagram like this. And by the way, if you know group theory, this is actually an example of a group action acting on the structure of all possible interval representations. So the structure you see is not completely random. Let's take a look at the 5 cycle, which we already know it's not an interval graph, so so the constraints are unsolvable. So we again start with a single P node with all the cliques, all the 5 cliques, because there are no constraints yet. Now we will add them one by one. So we start with U, which appears in A and E. Okay, so they're moved together to a common P node. Then another vertex is considered V, A and B. So A and B are put together, so we have to build a Q node here. And now let's continue in this way. So W is putting B and C together, so C moves into the Q node. Then X is moving C and D together, so D is merged into the Q node. But now the last constraint with Y is not solvable. D and E cannot appear next to each other. So this is unsolvable, and the resulting output is no, this is not possible to solve anymore. So we have seen this beautiful data structure, PQ-trees, which describes all consecutive orderings for the given input, and it gives us all possible interval representations. And whenever one tries to attack some problem in interval graphs, it is always a good starting point to consider the PQ tree. By the way, interval graphs are not only graphs which allow some decomposition like this one. For example, planar graphs, I have an example here, can be decomposed into something usually called in the literature as SPQR tree. So there is some tree whose nodes are much simpler, and whenever we are solving some problem, we can often just solve it for these simpler components, and then we can think of how to put the full solution together. So SPQR tree is very useful when one is attacking some problem about planar graphs. And in general, this approach of having a hard problem, so we will decompose it into smaller pieces, we will solve these pieces independently, and then we put everything together, is a really useful technique in mathematics. I want to conclude this video by describing one of my first mathematical results. It was a problem I did consider for my bachelor thesis in 2010. The idea is that before we were talking about recognition, where the input gives a graph G, and the goal is to build an interval representation for it. So for example, this would be some solution. I ask about a different problem where we also are given some intervals by the input. So positions of some of the intervals are already fixed for us and we cannot change it. And the question is whether we can add the remaining intervals. And in this case, the input graph is an interval graph, but the partial representation is so bad that we cannot complete it. Now we cannot add D, which is adjacent, which is intersecting B and C, but not A, because A is completely covering the intersection of B and C. So in this case, this input is not solvable. A partial representation extension problem is a type of partial solution extension problem where we are given already part of the solution fixed, and we ask whether we are able to still complete the solution without touching the finished parts. And this is well known from real life, that all types of of reconstructions are much harder than building everything from scratch. So for example, if you have an existing house and you want to rebuild it, you want to maybe add another floor or do some improvements, it's usually much harder than just erasing everything and building a new house. So, and this of course translates to mathematics as well, that these types of problems are quite often much harder. And in case of interval graphs, we were able to solve this. We were able to find a very nice characterization. So let's just consider the situation where two intervals are predrawn. So if we have just two intervals, if they would be disjoint and x appears on the left of y, we immediately know that all the cliques containing x has to appear on the left of all cliques containing y. So we get some partial ordering on the maximal cliques. Similarly, if there is a single overlap for them, we know that all the cliques with x are on the left of all the cliques with y, and all the cliques containing both of them appear in the middle. But in the last case, where one is contained in the other, not much is known. We don't know whether the cliques for y appear on the left or on the right of the cliques for x. So there are pretty much no constraints, except of course there is no clique containing just x. And so we have these three situations for two predrawn intervals, and of course then we can generalize to more predrawn intervals. But always we get some partial ordering on maximal cliques. And so what I was able to show in 2010, 2011, that these conditions are not only necessary, but they're also sufficient. A partial representation gives some partial ordering of maximal cliques, and it is extendable if and only if there exists a consecutive ordering which extends this partial ordering. So we have basically to check whether this partial ordering is compatible with the PQ3. Okay, but what is the definition for this partial ordering in general? So let's consider some predrawn intervals, all of them at the same time, like this. And suppose that now we have four maximal cliques. So we have a clique, which contains from these five predrawn intervals only uv. We have b clique, which contains only y. We have c clique, which contains both x and y, and d clique, which contains both y and z. And let's now draw where each of the cliques can be placed in the partial representation. So a clique can be placed only in the intersection of u and v, like this. B clique can be placed in two possible locations, either on the left of x or in between of x and z. The C clique has to be placed on the intersection of x and y, so it's sort of cutting B in middle, and D clique has to be placed in the intersection of z and y, so it's in the end like this. And now what we actually do is that we will just take the extreme points and we will create open intervals around them. So each interval, each clique is represented by some open interval. And now the main idea is that if some clique appears, if the interval appears on the left of the other interval, then we necessarily know that the A clique appears on the left of the B clique. So the triangle ordering is defined by that A is smaller than B if and only if the interval for A appears on the left of the interval for B. So the Hasse diagram for this particular case looks like this, that we know that, okay, A is on the left and D is on the right, and B and C are somewhere in the middle, but we don't necessarily know whether B is on the left of C or in the other way. So we are free, we don't pose any constraint there. And we were able to show that this is actually the correct partial ordering definition, that the partial representation is extendable if and only if there exists a consecutive ordering of maximal cliques which extends this partial ordering. And we can use PQ trees to solve the problem algorithmically. And so the situation is we have some PQ tree, say like this one, and we have the partial ordering described by a directed graph, like this. And we will just process the PQ tree from bottom to the top. We start with the subtree T1, having cliques A, B, and C. And for this subtree, we have just to find some topological ordering compatible with the direction of the edges. So in this case, we can just reorder them as B, A, C, like this. And then we will contract the subtree into a single vertex. Now, we will consider the green Q node. And there are two possible orderings, and we can just check both of them. So either DEF or FED. And we can use DEF, so we don't have to change anything, and we will contract again. But now we have to deal with the root P node, and this is no longer possible because there is a 2 cycle there. By the way, notice that the original digraph is acyclic, but it was not compatible with the structure of the PQ tree. So the instance is still not solvable. And this actually leads to a quadratic time algorithm, and with a lot of work, a lot of extra work, and dealing with a few more tricks and some details, we were actually able to solve the problem in linear time, but it took us a few more years. And so we have obtained this beautiful characterization of partial representations which are extendable. Just think about it, like we start with a partial representation, and then we use some constraints into it to build a partial ordering of maximal cliques, which is actually described by another interval representation. So there are two types of interval representations, one on the vertices, and the other interval representation is on maximal cliques. And actually this interval representation, this partial ordering is special. It is so-called interval ordering, which is sort of a dual term for two interval graphs. So these two things are closely related to each other. And I didn't have enough time to cover this part of interval graphs in this video. But yeah, so we have this really beautiful result, and also this was just the starting point for my research. So I have put, if you're interested in the details and maybe proof of this result, you can check my PhD thesis. You can find a link to it in the video description, or you can also check the presentation in OrgPad. And I was quite lucky that we were able to work on this with a lot of different people. For example, a couple years later, we were able to generalize Lekkerkerker Boland to partially represented interval graphs. So we were able to describe all minimal partially represented graphs which are non-extendable. And whenever you have a non-extendable partial representations, you can always find one of these patterns there. These are actually just a few patterns. The complete list is much bigger, but nevertheless it's solvable. And the paper has about 50 pages of detailed structural analysis, so it's non-trivial. And there were a lot of other results following this study, this question from my bachelor thesis. So I was working with a lot of researchers around the world, people from Germany, Poland, Japan, Canada, all around the world, and we were able to together solve the problem for a lot of different geometric representations and a lot of different problems. So it was a really great experience for me. Okay, so this was my presentation, so I hope you have enjoyed, and yeah, if you like the video, leave a like and subscribe, and if you have time, I recommend you checking this web application OrgPad I'm now creating. It can really help you to sort out your thoughts and be more productive and think better. Have a nice day.